We were discussing this atomization technique. It has got 4 subtypes. All these are the atomization techniques. We first discussed that was based on a high pressurized airflow that was used to disturb that liquid metal flow to disturb into particles and then let it settle down so that you will get the metal powders. The second technique, that airflow is going to be replaced by a high pressure water. So now the technique is going to be similar. From here at the top, we will pour the molten metal that will flow down still over here, and here that liquid metal flow will be disturbed by using the high pressurized water jet. So that water will or high pressurized water jet will impact the flow of liquid metal. It will disturb that flow and it will broken down to a smaller particles. That broken down particles will mix with the water, and that mixture will be created into the atomization tank itself. Okay, now before applying that metal powders, that water has to be removed, because whenever you use metal powders that are supposed to be in a dry condition, right? So that de-watering will be done. Water will be removed from the powders, and the powders will be separated and dried. So this is the second techniques that is used to get the metal powders. Then third one, it is a spinning disc technique. So what we do in this third technique, again same molten metal, it will be poured through this turn dish. Then when that flow reaches to this disc, this is a horizontal disc that is rotating at a very high speed. And what happens when this flow comes in contact with this rotating disc, the disc disturbs that flow, and it will distribute that flow into the particles, and that particles will be thrown in the outward directions because of the centrifugal force. So the flow will be broken down to particles will move axially outward, and those particles will settle down to a powder. So this would be the third techniques. This one is called as spinning disc technique. And reverse to that, in the fourth technique, here what we are doing, we are melting the metal first. That molten metal will be poured on this high speed rotating disc. And reverse to that, in this fourth technique, what we are doing here, the material rod that has to be converted into powder. For example, here we are using tungsten electrode because we are expected to get the tungsten powder. Okay, so there will be a metal rod that will be heated till it starts melting. And when that heated rod about to melt, it will be rotated with a very high speed. So there is one rod that is heated. So at this end, when it about to melt, it will be rotated with a very high speed. So what will happen? That melting portion will gets converted into particle, and it will be thrown away from the rod, again because of the centrifugal force. So that way you will get the metal powders. This whole operation will be carried out in the presence of inert gas. Okay, so this is the fourth technique that is used to get the spherical metal powders, and it is part of atomization technique itself, or it is another example of atomization. Now, out of all these four techniques, the most spherical particles you can get are with the pressurized air technique. Okay, so let it be this spinning disk or the spinning rod itself or this water atomization. The most spherical particles you can get with the first technique, that is in presence of pressurized air. Next technique to get the metal powders, reduction, or this is also called as chemical reduction. So what we do in a chemical reduction, as I said, the raw materials of metals available in the atmosphere are combination of metal plus oxygen, and this combination is nothing but metal oxide. So if I take copper, it will be copper oxide. If I take iron, it will be iron oxide, and likewise. And when I want to purify this metal, I need to remove this oxygen from that metal. And once I succeed to remove the oxygen from the metal, that metal oxide will turn into a metal. And to do that, what we usually do, we heat metal oxides at certain temperature, depending upon which metal oxide you are heating. We heat metal oxide in presence of gases like hydrogen, carbon monoxide, and these gases are called as reducing agents. So take a metal oxide, heat it in presence of either hydrogen or carbon monoxide. So what will happen? The oxygen present in metal oxide will react with this hydrogen or carbon monoxide, and it will be separated from this metal oxide, and you will get the purest metal. Now the metal that we usually get through these reduction techniques are going to be spongy in nature, more porous, and the particles are going to have uniform size. So almost all the particles will be having uniform size. There would not be a very small particle and there would not be a coarse particle altogether. All the particles are going to have some uniform size. To have better understanding of this reduction technique, let's take a look at this chemical reaction. Through this chemical reaction, you will easily get what we do in a reduction. So there is a copper oxide and it is mixed with hydrogen. Mixed with hydrogen means we put this copper oxide and hydrogen together and we heat it. So when you heat it, what will happen? Suppose, let's take example of this reaction. There is H2 molecule and there is one CuO. This H2 will react with this oxygen, and that way two molecules of hydrogen and one molecule of oxygen together forms one molecule of water. And what will happen? We will get the remaining free Cu, that is copper molecule. Okay, so that way you can get the powders, and this technique is called as a reduction. Next technique to get the metal powder is electrolytic deposition. In electrolytic deposition, what we do, we take one vessel, we put some electrolyte fluid in there, we emerge two electrodes. Those electrodes will be connected into the electrical circuit. One would be connected to positive terminal, another connected to negative terminal. And when you brought in the uh, metal oxide, that has to be converted to powders or purified. So what will happen if I take example of this CuO? If I put CuO in here, I will get Cu molecule and oxygen molecule separated. One will be positive molecule, another will be negative molecule, and positive will get attracted towards negative terminal, negative molecule or negatively charged molecule will get attracted towards positive terminal, and that way I can separate Cu and O. Okay, so this technique is called as electrolytic deposition. This process is to be carried out in electrolytic solution, or also called as aqueous solution or fused salts. So this is another technique. Next, carbonyls. This is another technique to get the metal powders. Here what we do, before getting the final pure metal or final powder particle, we first form carbonyl of that product. If I take iron, then this will be the iron carbonyl and its chemical formula. If I take nickel, then this is nickel carbonyl and its chemical formula. So what we usually do, we allow iron or nickel, whichever metal you want, to react with carbon monoxide. So when we let this iron or nickel react with carbon monoxide, you will get this either iron carbonyl or nickel carbonyl, depending upon whichever raw material you are using. And once you have got that carbonyl of the metal, iron carbonyl or nickel carbonyl, that will be allowed to decompose further. So what will happen when you allow it to decompose further? This CO molecule will escape or it will be released, and you will get either iron or nickel in its purest form. So when you let it decompose, the iron and nickel molecules you will get, and the molecules that you get through these techniques are going to be smaller in size, more dense, and uniformly spherical. Again, you will get spherical particles through this technique, and all the spherical particles are going to have uniform size. So there will not be a very small sphere and very large sphere. All the spheres are going to be have uniform size distribution. So that is the another technique, forming carbonyls of that particular material. Next technique, uh, comminution. So what we do in this comminution, there are three techniques. Just like atomization, we saw four techniques. In comminution, there are three techniques. What are those three techniques? First one is crushing, shown in the first example. Second one is ball milling, second sketch, and third one is grinding, shown in this third sketch. Let's explain one by one. First one, crushing. What we do in crushing, you can see there are two rollers, usually made up of steel or high speed steel. Those two rollers will be rotating, and the material that has to be converted into powder, that will be supplied over here. So it will be introduced, and when it passes in between the two rollers, because of the pressure exerted by those two rollers, or in short, those two rollers are crushing that raw material into a powder particles. So that is the first technique. In second ball milling, there would be one chamber. There will be one opening through which raw material enters the chamber, another opening through which milled powders or product goes out of the chamber. And in between, what happens? It will be half filled with steel balls. It will not be completely filled, it will be around half filled with steel balls, and it will be rotated about its axis. And what we do, from left end we introduce the raw material. When it enters into the chamber and this whole assembly is rotating, these steel balls will impact that introduced metal, and it breaks down into a smaller particles. And once that raw material has got converted into small particles, those particles will be taken out through the another opening. Okay, so this is ball milling technique. And third one is uh, grinding. So here what we do, there will be one rotating disc at the center of which there will be one link, and at the end of those two links there will be two hammers connected. So in this assembly, at the center, two rods are connected, and at the end of those two rods there are two hammers, and this whole assembly is rotating at a certain speed. So when it is rotating, the raw material will be fed from here. So when raw material enters this region, these rotating hammers will impact or have impact with that raw material and will crush it down, and that crushed powders will escape through these openings, and that way you will get the crushed metal powders. So this is the third technique or third example of comminution, through which you can convert raw material into metal powders. All three are the examples of comminution. Next one is mechanical alloying. This is the another technique that is used to convert raw material into metal powders. Now, this technique is exactly copy, or it is the same technique that we have used over here, that is ball milling. Same technique we are going to use for mechanical alloying also. So when you explain the operations, you can explain the things that we explained in the comminution itself. Now what we do in mechanical alloying, in ball milling or in comminution, what we do, we introduced a single material that was supposed to be converted into metal powders. Now in metal alloying, we know that we need to mix more than one material together. So instead of introducing single material, here what we do, introduce more than one material or whichever material that to be alloyed together. All the materials will be introduced through this opening, and remaining operation is same. This whole assembly half filled with steel balls, it will be rotating, and when all the materials enters this chamber, all materials are crushed together, and during that crushing and all, there will be diffusion of one material into another. So all the particles get alloyed here in itself, and you will get output as alloy powder, because individual molecule of that powder that we are getting over here is going to be a alloyed material, or that is combination of all the materials that we have introduced in. Okay, so that way you will get the alloy powder, and technique is called as mechanical alloying. Now, in addition to these prominent techniques, there are few more techniques that are used. Those are used rarely. So, we are just going to enlist those techniques over here. The additional techniques are precipitation from chemical solution, then uh, producing fine chips using machining. We know that machining or metal removal process, removing of the material from the raw material surface. Now, when you adjust machining parameters in such a way that the form chips are very small and almost of uniform size, then that machining could be used as a producing technique also. And last one is vapor condensation. So these are few additional techniques that are employed for the conversion of raw metal into metal powders. So these are the various techniques for metal powder production. So this is the first step. Now, before talking about the second step, let's discuss the characteristics of the metal powders. What time we have left with us? It is more than 10 minutes, right? Let's continue. So, what are the characteristics that are associated with the metal powders? First one is size, second one is shape, and third one is distribution. These are the third characteristics that are going to play an important role in characteristics of the product that you get as an end product of the powder metal processing. So when you convert metal powder into a final product, whatever characteristics that has possessed by the product are going to be affected by particle size, particle shape, and distribution. Distribution in the sense size distribution that we'll be discussing in upcoming slides. Let's begin with the first characteristic, that is particle size. Okay. So this particle size, how to get the desired particle size. We know that if you take an example, if I want to fill this box, if I use a very small particles, and if I use coarse particle, okay, if I fill this box with very fine particles, and in another case if I fill it with the coarse particle, and when I fill either of those two, and if I try to find the density, then density with those fine particles is going to be much higher compared to larger particles, because when you try to put large particles together, there is going to be a void spaces in between the large particles, free space in between the particles, and that is going to reduce the density. And if density is less, how that density is going to impact the characteristics or properties of the product, that we'll see in the upcoming slides. But at the moment, remember this, how the size of the particle is going to affect the density. So for that reason, we need to identify the particle size. And to identify the particle size, we have seen this example while discussing the first unit, abrasive machining. How do we get the particle size? That is in the form of mesh size. Mesh size means I will take a uniform area and I will provide some openings. So if I take example over here, it has got 25 openings, right? So mesh size is 25. So now if I use this sieve or mesh to filter the powder a large size particles can go through these openings, right? So through these sieves, I will get larger particles. If I take same area and if I increase the number of openings further, what will happen? Now the openings has got reduced in size. So if you compare the particles that can go through these openings and go through these openings, here you will get more smaller particles, right? So this relation we know, more the mesh size number, smaller the particles. Okay, that same we can compare over here. If mesh size is 30, particle size will be 600 micron. If I increase that mesh size to 100, 30 to 100, so particle size has reduced from 600 micron to 150 micron. If this 100 is further increased to 400, so now mesh size is 400 and particle size is 38 microns. So it got reduced from 150 to 38 microns. So that way we can identify the particle size. Now, in addition to this sieves or mesh size, there are few more techniques that are used to identify the particle size. First one is called as sedimentation. So what we do in case of sedimentation, we uh, put those powders in a, just a second. Okay, we have about 10 minutes. In sedimentation, what we do, we put those metal powders in a fluid. So there will be some liquid in which we put those powders and we measure the time taken by that particle to settle down. So if this tank is filled with some liquid and if I uh, pour some metal powders. If particles are larger, they will quickly settle down. If particles are smaller, a more time will be taken to settle down. And we will measure the time taken by particle to settle down. And depending upon the time taken, we will identify the size of the particle. Okay, if I had carried out the same operation in vacuum, we know that irrespective of its size, both particles we have will have settled down at the same time. But now this is filled with a fluid, so that is going to affect the time required to settle it down. The second technique is microscopic analysis. So in microscopic analysis, we apply techniques like transmission electron microscopy and scanning electron microscopy. These are microscopic techniques, and by using those techniques, we can analyze the particle size. Next technique is light scattering. So what we do in case of this technique, we uh, expose the powder particles to a laser. So when laser is focused on those particles, some light will get reflected or scattered from those particles, and those scattered particles will be detected by using some sensors, and that scattered light properties will be utilized to identify the particle size. So there would be particle that would be bombarded with laser, and reflected light will be sensed, and that will be used to measure the particle size. The next one is optical method. In optical method, that is quite simple one. What we do in case of optical method, there will be one source that will emit some light. There will be some sensor, generally a light sensor or photo voltaic cell, and in between metal powders will be placed. So what happens when individual particle comes in between source of light and sensor? It will create obstacle for that light to reach its sensor, and that will be characterized to identify size of the particle. The larger the size, it will produce a large obstacle. If it is smaller, the obstacle would be smaller one. That is quite simple. So that way you can identify the particle size. And last one is suspending particles in a liquid and detecting the particle size using electrical sensors. That is one additional technique. So all these techniques are employed to identify the particle size, and we know importance of particle size because that is going to decide density of the product, and density of the product is going to decide various mechanical properties. What relation is there, that will be discussing in the upcoming slide. uh, Particle shape. Okay, let's not go for this one because it has got 2 3 points to be discussed, and I don't think we can finish this one. So we'll stop over here. Akash, you there?
Yes, sir.
Okay. Uh, Tomorrow we have lecture at 10:30. But the thing is, I have got that vaccination appointment scheduled in the morning itself. So I don't think I could conduct tomorrow's session. So talk to other teachers and see if anybody is interested to conduct their session in the my slot. That is at 10:30 a.m. Anyhow, afternoon sessions are not there, right? Akash,
Yes, sir.
your voice is breaking. Can you? Okay, anybody else?
Yes, sir.
Okay, so ask somebody to conduct their session in the morning if anybody is interested. Okay.
Yes, sir.
Okay, so I'll stop over here now and we'll discuss this particle shape properties. Few properties are related to shape, that is aspect ratio is there, then shape factor is there, and then additional properties like size distribution and all. We'll discuss those things in the, uh, if possible, we'll conduct one session in this week only or in the next week. So I'll stop over here.